Thank you. Okay, right. Thanks for inviting me to this tutorial. Very, very important topic to understand more about video modeling. But just to put my talk at the right level, can you give me a show of hands whether you already work in video modeling or you're here to learn about video modeling? So show of hand if you already work in video modeling. So that is by raising your hand. Okay, familiar names, good to see you. Okay, we have a good amount of people, but not many. Okay, so I will not assume that people are already working in video modeling, but given the topic, if you feel this is going too slow or too high, let me know. So we have about 10% of people who have done video modeling before. Let me give you a little bit of a quick introduction into where we are in video modeling, where we want to be. And please stop me at any point in time for questions. So let's watch a video together, and this is from our dataset, Epic Kitchens, and I hope you can hear the audio as well. It's very easy to know what the person is doing, what their goal is, what they want to do. But in fact, in our, say, world of doing data-driven research, what we have is the following. We have these. That's what we actually have. And the video you've just shown, regardless of how small, is in fact about 500 frames. I'm not gonna bore you by showing you all of them. All of these are just 29 frames. That's what makes video until now significantly harder than other tasks. The fact that, we know what to do when we have a single image. We know the actual, background, which is we take an image in and we can put it into a model and we can make a prediction. What do we do if we have these 500 frames representing this very short clip? Okay, what we know what to do now at the moment, regardless of what you're talking about, even if it's CNNs or transformers, all these models to deal with video, they still need to select some sort of n frames out of these 500 frames. There is no model or approach or solution at the moment that takes all these highly redundant 500 frames. We all make this selection of frames that we believe are relevant to making a decision. That means we're throwing data. Very strange. Why do we throw data? We all want a lot of data, but this is highly redundant data. And most of our approaches in video, in machine learning in general, assume some IID data, that the data is independent from one another. So we don't really want to put too much. We want to sample just enough to recognize the action. So what do? Let's take our 29 frames and take a subset. 1, 2, 3, 4, 5, 6. Enough to know what the action is. And we then do whatever we need to do. VIT model, whatever approach. However, if we went a bit extreme, say if we went like this, 1, 2, 3, these 3 frames are not enough to recognize the action. In fact, video modeling is this chicken and egg problem. We need to select the frames to recognize the action, but unless we know the action, we don't know which frames to select. And we all, regardless of what approaches we do, are in this dilemma of how do we deal with this high dimensionality of videos. Many people try to do, multi-modality. So maybe audio guides you to where the frames are. Maybe we do some 1 frame per second and just ignore this frame selection problem. But in fact, that problem really exists. And in this talk, I want to tell you that actually we need to address this problem and address it head first. Really try to understand why we can't do some of the problems we currently don't even attempt because of the chicken and egg problem of sampling frames. So let's assume we want to understand what I call fine-grained understanding of actions. We want not only to understand that the person here is smashing garlic, but we want to understand when exactly was the garlic smashed. We can't get away with our sampled 6 frames, right? We need to do more. Or how exactly is the garlic smashed? Or how skilled is this person in smashing garlic? Or maybe exactly at this moment, has the garlic been fully smashed, or do we still need to do more? So the hypothesis here is by asking these fine-grained questions, we might really produce models that are not at this mercy of sampling frames. So what information do we need to answer such questions? We need to guide our frame selection. We can't just take random 6. We might want to think about change in appearance. We need to understand motion. We need to maybe include audio or other stuff. And maybe other information we haven't yet thought of. Maybe, by trying to answer these questions, we will realize we actually need depth. We don't know. But in not attempting these fine-grained questions, we're not really trying to resolve this chicken and egg problem. Right, so this is the premise of the talk. But before we do that, to be able to even answer or to be able to even ask these questions, we need some sort of a data set. And in my group, we really focus on these people interacting with objects using their hands. And we have the Epic Kitchens dataset. And I always tell people, if you haven't heard about the Epic Kitchens dataset, don't tell me. I'll be so heartbroken. So the dataset is collected by giving people cameras. It's publicly available in 2 versions. First version was available in 2018, and second last year, which we call Epic Kitchens 100. And this is a collaboration between the Universities of Bristol, Toronto, and Catania. And the idea was as follows. So we didn't start by saying we want to do action recognition and these are the classes. So let's collect examples of these classes. We went and said, let's collect data. And then we see what we can do with it. So we gave people cameras and we said, collect everything you can do in the next 3 days in your kitchen. Put this head-mounted camera, start recording before you walk into your kitchen, only stop recording as you walk out. This type of data collection is not usually attempted because people don't know how to label this data. It's just so many hours. Who would even label it? And part of the idea of Epic Kitchens is that we ask them people to watch their footage and to give us these live narrations of what they've done, from which we went and collected these action segments. So we basically made our annotations a lot easier because we started with synchronized live narrations. And first we released the Epic Kitchen version 1, which we now called Epic Kitchens 55, based on the number of hours, not the number of classes. It has 3,000 classes of actions. And then over the next 2 years, we went and collected an extension, refined our interfaces, improved our annotations. And now between your hands is Epic Kitchens 100, which is extremely long-tailed. That's the nature of the actual data collection because we don't have 100 examples of every class. So the y-axis here is log scaled. And this is in terms of actions. And you see the same in terms of objects. And there are 97 action classes and 300 noun classes. And their mixes are, the valid mixes. You can't break your tap, but you can open it, etc. And we have 5 ongoing challenges, which actually this morning we released the first set of winners. So this is fresh off the hop. This is the set of winners that received their awards today on these 5 challenges. And if you're interested, you can look at more details. I just want to show you the action recognition challenge because it relates to the chicken and egg problem we've just discussed. So the action recognition challenge, out of all these hours of recordings, what we have is a given start and end time. And you just need to say the person is opening an oven, right? So this is a classic recognition task. The data set lends itself to a lot more interesting things. And over the past few years, people have been submitting to the leaderboard and comparing challenges. But let's look at 3 seminal approaches and how they compare on this data set. And I'm going to go a little bit early in time. Well, not too early. So I'll start by 2016. And the first approach to understanding these long videos, and this was called temporal segment networks, TSN. You'll still see many papers compared to it as a baseline. TSN says, let's divide the video into a fixed number of segments, say 3 segments. Then we can randomly sample 1 frame from each segment. So at each point we have 3 frames, but we keep randomly sampling these, any 3 in training. We have a fixed set in testing, or maybe you have a few in testing, but we always expect that 3 are enough to be able to predict. So that's TSN. In TSN, the order of the frames, even though you always sample 3 frames, but the order of the frames isn't really preserved in making a decision. So many more people try to kind of order them. The next approach I want to say, that's 2 years later, and I'm selecting the approaches because we've evaluated them on Epic Kitchens, but you'll see a good number of comparable approaches around the same times. This was called TRN, which says 3 frames are not enough. So let's have combinations of 2 frames, any 2 frames, 1 and 9, 5 and 10, combinations of 3 frames, combinations of 4 frames, and train some models accordingly and aggregate them. That's a more powerful approach. And in this case, the input is a concatenated set of 2 frames, so order is preserved. And maybe a more recent one that's still kind of quite comparable to state of the art, is a temporal shift module, which again samples these frames in a TSN style. So you sample frames, but it does some sort of a shifting in the order of the channels, giving you an additional understanding that is stronger than previous approaches. So let's look at these 3 types of sampling approaches and how they compare. So this is from the first evaluation of the Epic Kitchens dataset, and we can look on the right side on certain actions, like, put plate and take plate. And you can see in this confusion matrix that these are not so well recognized when you don't have an ordering of actions. And these newer models which preserve order are improving the ambiguity at various rates. So good. Having some sort of an order is good, but still all these approaches are sampling frames in some way or some manner. And if you're interested in playing with some of these baselines, we have released models and code for our dataset on some of the popular benchmarks: slow, fast, TSN, TRN, TSM, and TBN, which is something we proposed 2 years ago now. Okay, so I'm not going to talk more about Epic Kitchen specifically. I want to go and ask these questions, which we said are going to be quite instrumental in improving the way we do video understanding, because they will hit the nail on the head and ask questions that are related to exact frames to be able to answer them. This is all the works we've done around this area. I'm not presenting all of it, but these are all fairly recent works. I made this selection to answer, and then I'll stop after each section for questions. And let's start by skill determination, which is how well are you performing a particular task. And the task is easy, which is I have 2 videos, and we need to decide which one is performing the task better. It's the same task, and you can have easy annotations here. You can give people labels and say which one you think is good, and hopefully they will agree that the person on the right knows how to draw better than the person on the left. So what do we do now in terms of trying to understand this level? Okay, we take these 2 videos, and then we go and extract dense features throughout the video. So we're trying to put everything in. We put it in this case into i3D, which is a 3D convolutional network. And then we can average the decision, global pooling, in this case, global temporal pooling. And then we can train a model that aims to give the first video a score higher than the second video, purely based on the ranking. But we will have all possible pairs. So hopefully by the end, we will end up with a list that matches our labels, and hopefully it will generalize to the test set. So these 2 are shared weights because we need to give a video eventually in and be able to predict its score. Of course, not all parts of the video are equally important in doing skill. In this case, this is a person braiding hair. So at the top, you'll see lots of actions of the person that are not relevant to skill, combing hair or preparing. All of these are not relevant to skill. So we need to weight these different video segments differently. We don't know which parts of the video are relevant. So we introduce some sort of a learned weighting, right? We can introduce an attention model or module that learns to basically give different weights. And in this work, if you want to read it from a couple of CVPRs ago, we also added some sort of a loss that allows this to always outperform average and gives it additional stability. So we did this task and we said, great, now we think it will work. And it indeed gave good results. But when we were looking at the parts of the video that had been picked as evidence of high skill or low skill, we realized that mistakes get very low weighting. So mistakes don't get picked up as the part of the video most significant to deciding skill. That's very weird because that's how a human would say, oh, that's a mistake, so I will lower the mark. And that's in fact because of this shared weighting architecture, which had been used for ranking approaches for a while, but it's designed to only focus on the bits or the parts that are present in both pairs of videos. So in this work, we propose to use multiple temporal attention modules. And up till now, they are both exactly the same until we have a specific loss that trains them to attend to what's good in the video and what's bad in the video differently. By adding these two attention modules in this case, but you can add more, we can go and look at what the system had learned for a specific task. So you can see here a selection of what was labeled as evidence of low skill in a variety of tasks, and this is learned by the model. So in the second line, you have people undoing parts of the makeup. This is a good evidence of low skill. In the origami case, you have people unfolding, and again, this is evidence of low skill. While when we look at high skill, you see people firming up their origami as evidence of high skill, and evidence of pausing to think in drawing, and that is evidence of high skill. So if you hesitate and stop in drawing, it's high skill. But if you hesitate and stop in cooking, it tends to be evidence of low skill. That's sweet. That's nice to know that the model can learn something by attending densely. But this can only be done currently on a single task. Right. All the works I present, if you're interested, you can go and look at the papers, look at the data sets and the models. Another question we were trying to ask, and again, we all are aiming to answer these detailed understanding and whether this changes how we look at our temporal models. So this is a scene from the Ellen show. And in this part of the show, people are shown a video and they were asked to predict whether they believe the person is going to succeed or fail in the task. So they put this board up and they predict, whether the person is going to succeed or fail. Now, if I give this video to any current benchmarks that we have, it will say this is a person who is playing basketball or shooting basketball. We don't even ask whether the person has actually succeeded or failed. This is not a task we currently do or think about. And this is from HMDB, which is one of the most established data sets in video understanding a while ago now. So in this class, which is blowing candles, you see two videos. The video on the left, the person blows the candles and successfully puts them off. But the person on the right, this poor kid keeps blowing the candles and one of these candles that don't go away. So what you'll see is a comparison between the method I'll show you and the ground truth. And this is before completion, before the person blows the candles, and it turns purple after the person. While on the right side, it will say all the way till the end, the candles haven't been blown. And it's very interesting to think about this problem because this is not a localization problem. We don't even know if completion happened. So we can't say score the highest value because we don't know if even it happens. So it's a combination of a classification and a localization task. And we're targeting a certain frame. So again, we need to think about a dense understanding of the video. So what did we do in this case? And Farnoosh, who now finished her PhD very successfully, she came up with this idea that each frame in the sequence should contribute to the understanding of completion. So any frame will go and say, I believe I am pre-completion, or I believe I am post-completion. And this evidence from all the frames will help us decide where we are. Are we completed or not yet? If all the frames keep saying completion is in the future, then all the way till the end of the video, there is no completion. So that's what we did. So we had a frame going in, some sort of a convolutional network, a recurrent network, so it knows the past, doesn't know the future. And what it does is one of two possible solutions. the frame itself can predict that it's post-completion, and accordingly, it votes for all frames in the past as potential completion moments. Or the frame would be pre-completion, and then it would vote into the future. And this is voting that doesn't know when completion will happen. It can be more intelligent to vote when in the past or when in the future the completion will happen. And in this paper, we showed how you can accumulate these varieties of votes using either a classification or a regression decision. And the paper shows that if you're predicting in the future, you don't have a good estimate of when, but if you're predicting about the past, because it's a one-directional LSTM, it's a good prediction. So there's a combination of the two, and we were able to show that you can predict moments when people do ordinary tasks, like when do you think the person drank exactly from the bottle, or when did the person pick something up from the floor? Okay, so this is the first set of things I'm going to tell you about fine-grained understanding. Check how are we doing with time. We are halfway through, I believe. So if there are any questions, raise your hand before I go into the next set, and you will get lost. Hands up, hands up. Your chance is gone. You have after the next quarter, you might ask questions if you want. So what else can we do? We can also think of videos like this, and this is after we're now trained to do action recognition. So I'm going to show you a video and ask you to tell me what is the action. So I hope you all agree that the action is someone closing a box, and this is from the something something dataset. In fact, this video never existed. This is the video that was recorded, and what I showed you is a reversed video in time of what has happened. And this is very interesting because time, when it comes to videos, has always been thought of as impossible to reverse. And in this work, we show that in certain cases, you can revert these videos, and a human wouldn't even be able to distinguish whether the video is actually in forward or in time. Don't think about most videos you see, which is you have waterfall and then the video is going upwards. Think about someone actually moving the handle from the left to the right. This is a reversible task. And sometimes you can reverse the video and end up with an example of a completely different class, like the closing and opening I've just shown you. And of course, there are things that are irreversible, and these are very well studied. We're talking about the first two. In fact, in this work, we showed that you can train using zero shot, using this duality of reversing. So for example, you take videos of burying something in something, you reverse them, and you use that to train for digging something out of something. You've never seen an example of this. You've only seen the reverse videos. But in testing, you're going to test the true examples. So the testing is exactly the same. It's just that the training is done by time reversing. And using a subset we have shown here, this is actually doing pretty well. You can learn how to open something by closing it. You can learn how to put something into something by pulling it out of, etc., etc. Look at the paper for more details. A work that will be presented tomorrow, I believe, tomorrow in CVPR, is on Fewshot. And Fewshot, again, gives you an interesting insight into actions. So for example, can I learn an example of someone cutting purely from two examples? And the Fewshot setup goes as follows. You usually have a query, and you have a few examples of a few classes, and this is called the support set. So in this example, you're going to see three-way, so three classes, two-shot support set. And you want to learn a classifier. All prior works to do with Fewshot, what they do is that they take one of these videos and they compare it to the query. So they compare the query to each video independently. In this work, inspired by two ideas, one that comes from images. So this is the cross transformer from images presented in ICLR last year, where you look at the query, you take a patch and you try to compare that patch to all patches in the other images. But videos are not about patches, videos are about motion and transformation. So borrowing the cross transformer idea with the TRN concept that I just showed you, the idea that you can represent something as pairs of frames or three tuple of frames or quadruple of frames, What we have is something that looks at a query video, then takes a pair of frames, so all possible pairs of the query video, and all possible pairs of the support set, and does a cross transformer. So it actually tries to find matches between these. Does a softmax, and then puts the query again into a linear map, and then gives you some sort of a prediction of how similar is all your pairs to all your pairs in the support set. And you can do that for pairs, for triplets, for quadruples, and come up with a good solution for all. This is in fact currently giving the state of the art on all possible Fewshot benchmarks. We have code out there and models, and Toby did a great job in preparing a code that hopefully you can easily use. If you want to know more, please talk to Toby tomorrow in session 1. Right. Another chance to ask questions. Let me tell you then about things to do with vision and language. So I told you about how to focus on fine-grained when it comes to maybe a few examples or maybe skill understanding. But language gives us a good understanding to do fine-grained. So this is a work from last CVPR where we looked at adverbs, trying to figure out whether we know if something is being turned slowly or diced finely. To know whether something happens slowly or quickly, you can't really randomly or guess. You really have to look at the individual frames. And in this work, we went down a slightly different route, inspired by maybe the more recent advances at the time. So we look at a video and a parsed sentence, and we aim to predict, or an embedding space, to learn an embedding space. We're given the embedding of the verb rolling and the video. We want to predict a modified version of the verb rolling, so it becomes rolling quickly. So there are two modified versions, say rolling quickly and rolling slowly. And we need to learn that modifier or that transformation in the space and learn it such that it's close to the video showing rolling quickly. We also learned this in a weakly supervised manner because we didn't want to go and ground truth all these rolling quickly in the how to 100 million data set. So what we did is that we took some attention mechanism. We used the verb as our query. So we know it's rolling. We're searching where is it in the video. And then we're predicting that to be close to rolling quickly. And everything is learned jointly. So the embedding space and the attention are learned together. And this gives us a very cool understanding. This is you can call this early work because no one has done adverbs before. There was work on adjectives that had inspired our work. But then what we can do is we can look at a video like this, and we can first attend to when mixing can happen. And this is the thickness of the border that you can see. And after the action is, say, localized, we can then predict that it is quickly. And then we can predict things that are being mixed quickly versus being mixed slowly. We can predict other types of actions, rolling slowly and rolling quickly, turning slowly and turning quickly. So again, we're waiting for the moment of the turn. And once we have that, then we can predict out of currently 6 possible adverbs. Another work to be presented in CVPR this year is related to thinking about videos and captions. So language and visual. And I believe you've seen at least 2 works until now, 2 presentations, keynotes on language and video. And we have to be a bit careful when it comes to using some of the video datasets currently. So these video datasets have a video and a set of captions, and they aim to predict that it is this caption that relates to the video. But in many of these benchmarks, what you see is a long list of actions where all these actions are in fact relevant. In fact, I don't know which one is more relevant to the video. They are all equally the same. But the ground truth of these datasets say one of them is okay and another is wrong. If your method is predicting a demonstration of origami, it will actually say, oh, the method isn't doing well. And in fact, if you want to know more about this, look at session 3 and talk to Mike about how we try to solve this and how can you improve this video understanding benchmarks when it comes to retrieval. Right, right. So this really shows that you can have, I'm just checking time to decide. Okay, I'm going to skip this. Talk to Mike about how you can do semantic retrieval with a much better approach so you can avoid this mistake of assuming that the video has only one caption. I'm skipping everything to do with audiovisual, and this is a marketing for my talk a little bit later on sight and sound, and go into a very, very important aspect of video understanding and fine-grained understanding, which is explainability. If we don't understand what our models are doing, we don't know whether they actually need fixing. And in this work, which we presented last ACCV, we looked at a video. We gave a video to a model, and we know that we will be able to predict how well is this video performing, and we can then think about the video as a one entity. But we want to understand the frames themselves. Note, before you get too excited or confused, this is an attribution method. So we want to analyze rather than train a model. So what we do is we take these frames and we take the model's prediction. So this one on the right, and what we want to do is we want to divide this into the prior probability. So if I haven't seen any frames, I will predict this class with this prior probability. Once I see some frames, I will increase my confidence, but these frames don't contribute equally to my decision. In fact, some frames are more significant in my prediction, correct or wrong, than others. So in this work, we looked very detailed at every frame and its contribution to the decision. So we start from this prior probability. We add one frame and we see the model's response. We add another frame and we see the model's response. And what we look at is the difference between these responses, and that differences can only be attributed to this added frame. But of course, you can sample many frames. So we had to do an efficient way to try all combinations to understand the impact of this particular frame. And the work is inspired by lots of approaches in game theory. And there is code out there for you to play with. But more importantly, I want to show you a good demo. Equally importantly, sometimes adding a frame results in the model's response actually getting worse. So sometimes getting rid of some of the frames because they're ambiguous or because they're more similar to other classes, they in fact have a negative contribution to the model's response. So let me give you an example. Again, this is from the something something dataset. And what you see are frames and their contribution to the class showing that something is empty. And in fact, the person is being too keen, so he's flipping and showing again. And in fact, these frames in the middle are being predicted as having a negative impact on the decision of that particular class. We have a public dashboard that lets you look at something dataset, so you can choose the dataset and actually decide which, look at the attribution of every frame. But very, very recently, hot off a press, Tom, who's an intern who's been working with us on the summer, has been trying to produce this dashboard for Epic Kitchens. And very, very interesting outputs. This is not yet there, but I'll be able to show you a first demo of it. So if this is an open drawer, what you're seeing here is the attribution of every frame to the verb and to the noun classes. So in the opening example, what you'll see is in fact, sorry, I went too quick. To the opening example is that nearly all the frames contribute equally to the verb prediction. Maybe at the end there isn't much motion. But in terms of the noun, actually, the more you see of the drawer, the more you're confident of that particular noun. So that's also interesting to think about how our actions are being done, is that sometimes to predict the verb, you need to look at different frames than to predict the noun. And this is a good example from our data set on closing a fridge. The example is in fact being predicted as opening a fridge. But if we look at the exact frames, we look at, in fact, as we go from one frame to the other, you can see that the confidence, actually the person is starting to close, but then opening the fridge again and then closes. The start and end times are right, but the person is doing multiple things. And so actually in this case, the selection of the frames is too critical. And using the dashboard, we can change the number of frames selected and we end up with a different classification. So if we select 6 rather than 8, we predict closing fridge completely. If we select 4, we predict taking something from the fridge. Okay, I want to show the next one, which is this one. Again, a very cool idea, a cool visualization. This is predicting cutting tomato. And in fact, every peak in the verb prediction is related to the person having the knife cutting, and every valley is the person actually moving the knife or preparing for the next cut. So our models are great. They're able in this case to predict the exact frames that are relevant to the cuts. And it's saying throughout, I am able to see the tomato. So it doesn't matter to make the noun decision what to look at. Lots of insights can be done from these attribution approaches, which we did not have before. And if I can, I'll be able to show you a live demo if I'm given a few more minutes. But I'll make my conclusion and then switch to the dashboard. Videos are made of highly redundant frames. Knowing which frames to select to understand the video is a chicken and egg problem. One of the ways forward, or at least the way I advocate, is to ask some fine-grained problems which can show the potential of our models and can give us lots of insights, including using attribution approaches. And there are a lot of open problems. So if you're here to work with video, now is the time for you. And I want to acknowledge the team and say, I'm happy to answer any questions now or later, but I will take one moment to show you this live dashboard. Okay, let's hope this will work. So this is the live dashboard that we will be able to actually share later. So this is a person, I don't know what this is, closing a drawer. And again, this is the conflict I told you between verbs and nouns. So at the very beginning, the verb at the very end is a lot better because it's capturing the closing motion. But by this time, the drawer is closed that I can't decide what I'm doing. So if you want to look at the noun, the first few frames are more significant to making the decision. And you can play with a variety of these examples and see this is an example of closing a drawer, but it's being predicted as closing a cupboard. And if you look at why this is the case, you see that at the very end, you lose the visual of the drawer and you have lots of visuals of cupboards. Our models are not bad. In many, many cases, what we're asking them to do might be too hard. And we need to think again at a completely different way of taking frames or segments and understanding the content of what they are doing. And I believe I am on time.